Welcome friends, welcome dear students. Myself Dr. Ajay MLT from Gadwal University again with you, this time with the lecture on polymers. Let's discuss polymers in novel drug delivery system in this lecture. In the previous lecture we had discussed the concept of NDDS, concept of targeting, that targeted drug delivery, passive targeting and active targeting we have studied in our previous lecture. So today we are going to discuss the polymers, which are the vital element of novel drug delivery systems. Now let's discuss polymers. After completing this lecture, you will be able to classify the polymers and select suitable polymers for novel drug delivery systems. We will cover this lesson under the heads definition of polymers, classification, selection of polymers, examples and applications we will be discussing in this lecture. Let's see, what are the polymers basically. Polymers are single monomers joined together multiple times to form a polymer. So they are single units, blocks you can say. When you join them, it becomes polymer. So when two monomers are joined, they are called dimer. When three monomers are joined, they are called trimer. When four are joined, they are called tetramer. 5 pentamer and so on. When the units joining together are ranging from 30 to 100, we call them oligomer. And in general, when these monomer units which are joining together are more than 200, they are called polymers. Then what becomes when 200 more than 200 monomers join together, they are called polymers. So as you can see, monomers with the process of polymerization become the polymer. So this may be the process of polymerization, may be addition, condensation or any other. So you have seen in the previous GIF that what was happening. Take a molecule of styrene. Let's see once again. Then when they join together, they form the polystyrene. And these are maybe of several types. Now let's discuss what does the polymer means or how we can classify them. We can classify the polymers on the basis of origin or source, structure, heterogeneity of monomers, or there may be several other classifications. Firstly, how will you classify the polymers? On the basis of its origin. It may be natural, semi-synthetic and synthetic. When the polymer is obtained from a natural source, whether it is a plant source, animal source, marine source, it is called natural, like cellulose, guar gum, gums like xanthan gums, chitin, alginate, etc. These are natural polymers. Semi-synthetic polymers, which are slightly processed natural polymers like hydroxyethyl cellulose, hydroxypropyl methyl cellulose, HPMC, chitosan, etc. Synthetic polymers, polyethylene glycol, polylactide glycolic acid, PLGA, polyvinyl alcohol, PVA, polyvinyl pyrrolidone, PVP, polyacrylates, etc. So this is simple classification you must learn. Whenever a polymer is asked, certainly definition and classification is always asked. Okay, now let's take another type of classification on the basis of structure. Polymer may be of three types on the basis of structure. They may be linear, branched, or cross-linked. Linear, as the name suggests, it may be a linear molecule, okay, joined one joined in series in single chain, linear. PVC, polyvinyl chloride, polythene, etc. Branch chain, in the branch chain, when the linear molecule is having one or two branches there, they are called branch polymers. So they are low density polythene is the example. Cross linked, they are the cross linking of polymer. When the several branches are cross linked put together, they are called cross linked polymer. They are basically somewhat like macromolecules like melamine, bakelite, etc. Now, on the basis of monomer, heterogeneity of monomer, we can classify them in two major classes, homopolymer and copolymer. Homopolymer, as the name suggests, there are two kind of monomers which are of same kind. Two same monomers in the entire chain is there, then we call it homopolymer. And copolymer are at least two different monomers are there in chain. In the entire chain, when at least two different monomers are there, we call it copolymer. And these copolymers can be of several types like random, alternating, triblock, and graft. See the examples of each and every subcategory. This you have to learn. Okay. Now, classification of polymers. I'm giving you a homework. Okay. What is the homework? Search and note down the classification based on biodegradability. There are two kinds of polymer: biodegradable and non-biodegradable. You have to check it out. Okay, and list them. On the basis of thermal response, okay, on the basis of mechanism of polymerization, addition, condensation, remember, internal structure or habit, okay, crystalline nature, amorphous nature, or maybe some other types, pH sensitivity, and water solubility. These are some basis of classification which you must know. That on the basis of these points, do you know about the classification of the polymers? If not, learn it, note it down. And it is utmost important, especially for the PG students who are going for formulations in their PG dissertation work and even for their practical works of this subject. It is utmost necessary to understand this type of classification and also to select the polymer for the drug delivery. Now let's discuss properties of polymers. When we are aiming for delivering a particular drug in a particular novel delivery system, what we need? We need a polymer. And what should be there in polymer? We should study what kind of properties a polymer should have. What you will have to check. Ideal properties we will check it later. Okay. This time we are discussing that first thing to check is molecular weight. Why molecular weight? Because molecular weight governs so many properties. Number one, the bioadhesion. In general, higher the molecular weight, higher is the bioadhesion or mucoadhesion, especially when you are going for the mucoadhesive or bioadhesive drug delivery systems. Can you have the example of this thing? PVP K30, K17, K90. You know the average molecular weight of K90 is maximum, 70 is in between, and K30. Okay, K30 is having only 40,000 Dalton. So K70 having the higher molecular weight shows the higher bioadhesion. In the same way, carbon 934, 972, 972 with higher molecular weight shows the higher bioadhesion. Moreover, the metabolism. The metabolism, you can say the low molecular weight drugs are metabolized quite easily as compared to the high molecular weight drug. Okay. Swelling. Molecular weight also governs the swelling properties of the drug matrix in many ways, and this swelling property in turn leads to the manipulation or the change in drug release. So molecular weight is associated with several factors. So first you have to consider that what kind of molecular weight polymer you should take. Viscosity, like we mentioned, that viscosity is responsible for swelling, matrix formation, biodescent, etc. Okay? Like sodium CMC, low viscosity, high viscosity, two grades are there. Which grade to take? So that viscosity is another parameter. We will discuss it again when we will be discussing sodium CMC a little bit. Crystallinity, ADME, absorption, distribution, metabolism, excretion. This pharmacokinetic is changed when the crystallinity of the polymer is changed. Onset and duration of action is changed on the basis of crystallinity. We have discussed in pre-formulation also. You might have studied that crystallinity governs the onset and duration of action. And so, in case of this polymer. Now, glass transition temperature from one phase to another phase. Okay, when it is melting, you can say nearby one phase to another phase, gel to cell transition, that temperature indicates the stability and interaction with the drug. So this temperature must be checked when you are preparing a delivery system. It may be indication of incompatibility also when the drug is interacting with the polymer. Okay. HLB, hydrophilic lipophilic balance. You know about the HLB? If not, please mention it. Please recall it. Okay. Formulation, compatibility, stability, and drug release. For all these things, we require a good HLB. That HLB must be fit to formulation. The next important thing is chain length and flexibility. Longer the chain length, higher the biodescent, up to a certain length. You cannot say that a whole long polymer chain will be biodesive. No, then the steric hindrance or other factors will work. So in optimum length in general. And flexibility, the polymer chain's flexibility also governs many things, including the biodescent and release properties sometimes also. Okay. So, polymer chemistry or knowing about the polymer is entire science. There are people do the MTech in polymer sciences. It's an entire subject. Okay. So what you need to do, you will have to pick up those things which is very much concerned to you, very much important to you with respect to your formulation development. Okay. Now let's move to the ideal properties of polymers. It must be stable, safe. It must not produce any adverse drug reactions. It should be non-reactive, non-toxic, and compatible or capable to modulate the drug release as per the need. Now the polymer is the driver which is taking the delivery system or which is governing the overall journey of the drug to the site of action or maybe site of measurement. It must be compatible with the drug. The compatibility of the drug with the polymer is utmost necessary. And it must be fit for the NDDS and targeted drug delivery. Okay. The ideal properties which is desired in NDDS and TDD must be there in that particular polymer. Now, how we will select the polymer? Let's discuss an important aspect, the selection of polymer. Factors which govern the selection of polymer include, first of all, nature of drug. What is the solubility of drug? What is the reactivity of drug? Physicochemical properties of the drug. You will have to see these things, even the lipophilicity or you can say partition coefficient you have to see. Okay. So pre-formulation you have done with the drug. So most of the time you know everything about the drug. You just have to match them with the with your need and the polymers available. Type of products. What kind of product you want to prepare? It is also important factor, like what kind of drug delivery system you want to prepare. Routes of administration, in which route, through which route you are going to deliver this delivery system. It also has the decisive role in selecting the suitable polymer. Now, another factors include types of drug release. Now, what kind of drug release you desire? What kind of control you want to have on the pharmacokinetic? It is also an important factor. Site of action, SOA. What is your site of action? Whether it is a RAS organ, whether it is a non-RAS organ, or it is a a tumor or any other organ. So depending on that site of action, many times you select a particular delivery system. For particular delivery system, you choose a particular polymer. Availability and cost, there are the two important factors. Which is not available to you, you can't go with that polymer, obviously. And cost effectiveness must be there. And there are so many factors, but I have just listed a few which are very important with respect to you. So just learn these things, and these are very much important. Selection of polymer is utmost asked. It is always asked in the theory, that what are the classification of polymers you will have to give, what are the polymers, and how you select the polymers. With the classification, you also get the question that how you select what are the criteria you select the polymers. The blending, how you do the blending. Okay. Now let me give you some simple lab tips. It would be very useful for your practical work, for your practical project or dissertation work. Now, availability is the first and foremost point. When we are working in the academic research, when we are working in our institute, first we will have to procure and ensure that this polymer is with us. And don't go for a polymer which is in literature and which is not in your reach. It would be futile. Though the polymer may be very fantastic, very good for your work, but the availability, the cost is very important factor. First of all, you should ensure the availability. Second, know the solubility of drug and polymer. You must know the polymer and drugs solubility, and then compare the things with the final products. Consider the things with the final product and what kind of release you want. No? Then refer the literature. Then you should, when you are having these data, then refer the literature. Conclude that what can be done with the available polymer, properties of drug and properties of available polymer. Hit and trial. Now use different ratios of drug and polymer and try. That hit and trial must be on the basis of literature review also. You cannot take any vague percentage of vague concentration. Okay, so that's why I'm asking you to refer the literature so that you can have an idea that in which concentration it is being used in general. Understand? Then when you done the hit and trial, make a blend of polymers. Why I'm telling you, because if you will take only one polymer, it won't give you much control over the drug release. Say for example, my drug is a hydrophilic drug, say for example diltiazem hydrochloride. Okay, and I am preparing a delivery system with the ethyl cellulose, which is a water insoluble drug polymer. Here drug is water soluble, drug is diltiazem, ethyl cellulose, water insoluble. If you will put the drug into the you will blend this drug, you will mix the drug, or you will prepare the delivery system with the ethyl cellulose in the with diltiazem hydrochloride. What will happen? The delivery system will be prepared, no issue. Okay, what will happen? The drug won't be able to come out of that system, because that polymer matrix won't be dissolving, won't be allowing, because it is water insoluble. So it won't be dissolved into the GI fluid or into the systemic fluid or into that any biological fluid where it is inserted or where it is administered. So what will happen? The drug won't be able to come out of that matrix. So what's the use? What now we have to do? We will have to make a blend of hydrophilic and lipophilic polymers. Now you take some amount of hydroxyethyl cellulose and some amount of sodium carboxymethyl cellulose, which is a hydrophilic polymer. You take ethyl cellulose, no issue, but you add some sodium CMC, provided it is compatible with the drug. Okay, then make a blend of that thing and then put it. So what will happen? That the controlled release of the drug will be ensured, because ethyl cellulose is ensuring the slow release and sodium CMC is allowing the slow diffusion of a drug across the matrix to the circulation or to the body. So go ahead with this kind of approach when you are doing your practicals. It is utmost important, and I think it will solve your problem, practical problem of selecting a suitable polymer for your drug delivery system. Now, let me give you an idea about the application of polymer. They are useful in day-to-day in life, in conventional dosage forms, in binding, disintegrating, coating, and other purpose. Polymers are the key to success in formulation development, specifically in modified release dosage forms. Polymers are fabricated as per the need of the NDDS and targeted drug delivery. In formulation development, in tablets, you add polymers as binder, disintegrant, release modifier. In capsule, in shell manufacturing. In preparation of emulsion, suspension, gel, modified release tablets, cream, gel, hydrogels, etc., you add the polymers. In preparation of various NDDS like transdermal films, microcapsule, microsphere, nanoparticle, liposomes, you need the polymers. In modifying the drug release, it is utmost required. The kinetics and bioavailability of drug is ensured with the help of polymers only. In targeting of drugs to specific organ, region or tissue, you require a suitable polymer. Now, take an example of matrix forming agent for hydrophilic matrices. Examples include hydroxypropyl methyl cellulose HV grade. HV means high viscosity grade. PVP polyvinyl pyrrolidone. Sodium carboxymethyl cellulose SCMC, alginates, xanthan gum and locust bean gum combinations, and carbopoles or carbomers. These are the matrix forming agents for hydrophilic matrix. Now, how it is formed? Mechanism. Polymer, when dissolved in water or get in touch with the water, it swells. This swollen network, that this water may be a biological fluid. Swollen network, it is formed in the presence of a cross-linking agent. They swell in water but can't dissolve because of stable cross-linking. They imbibe the water, swell, but they don't get dissolved into that thing. Understand? Because cross-linking is there. It is like, just like you can say, sponge ball which is having the water, but it doesn't dissolve it. It may be bigger in size in some cases, but it is not going to dissolve because it is having cross-linking there. Okay. They are used for formulation of floating tablet, implant, etc. They help in prolonged release of drug. So this hydrophilic matrix formation, due to the specific matrix forming capability, can be utilized in various ways in no drug release systems. Now, what are the modified release dosage form? We have discussed. Let me remind that as per the USP, modified release dosage form, it is defined as one for which the drug release characteristics of time course and or location are chosen to accomplish therapeutic objectives not offered by the conventional dosage forms. Learn this definition verbatim. As you can see in this graph, conventional dosage forms, peak and very effective there, control release is having that temporal control. SR, again, this similar kind of control there, but that peak and very effect is not there. We have discussed in drug targeting. Just to remind, drug addiction protocols are simplified with drug targeting. These are third generation dosage forms, and they have the spatial control. Okay, drug doses greatly reduced and drug therapy cost is reduced in case of drug targeting. Now, drug targeting advantages, we have discussed that a man will be happy, a person will be happy only when the drug will be localized into the site of action only, in comparison of the entire or peripheral distribution of the drug across the body, even to the healthy tissues. So drug concentration in target site is increased with the drug targeting without undesirable effect on target site. Okay. So drug targeting, I'm again reminding you this definition very quickly, that drug targeting is the ability of the drug to accumulate in the target organ or tissue selectively and quantitatively, independent of the site and methods of its administration. This is called drug targeting. Okay, got my point? We have discussed the definition. Please learn it verbatim. enteric coating. Now, what is enteric coating? Examples include, first I will discuss the example like cellulose acetate phthalate, hydroxypropyl CAP, we call it CAP sometimes. HPMC, hydroxypropyl methyl cellulose phthalate, these are phthalates are there. Copolymers of methacrylic acid and ethyl esters, polyvinyl acetate phthalate, okay, PVA phthalate, do not dissolve over the gastric pH range. These polymers don't get dissolved in the gastric pH. They dissolve readily, at least in the less acidic environment, and they require above pH 5 for dissolving. So they get dissolved only into the intestine. So we can prepare what we prepare, EC aspirin we take, EC aspirin. Many cardiac patients take the aspirin enteric coated, related aspirin. It is having an enteric coating on the drug, in the drug, so that tablet or the dosage form don't get dissolved into the gastric region. It dissolves in the intestine only when it reaches to the pH of intestine. So gastric will be having the 1 to 2 pH. So when it will move, where the dosage form will move to the intestine only, there only it will get dissolved. So what is the advantage? The gastric irritation caused by the release of the aspirin into the gastric region will be avoided in this case. Okay. Colonic delivery system. Now we want to target the colon. pH sensitive polymers are there. You can have the pH sensitive polymer like combination. We have given you the homework of pH sensitive polymers. Let me give you something that your combination of Utrajit 155, which is pH 5.5, and Utrajit S, that pH 7. You can have this blend of polymers, one or more polymers you can take which are sensitive to the to a change in pH for their degradation and the release of the drug. To coat the drug or delivery system with a polymer that is sensitive to bacteria in the colon, it may be alternative strategy. Or degradation of the polymer permits release of the active drug. In this case, the polymers like glassy amylase mixed with ethyl cellulose, azopolymers. Azopolymers is a group of polymers which are cleaved they only by the bacterial the bacteria present in the colon. So they will be releasing the drug only at the colon. So colon specific delivery can be done, and it holds true with the guar gum and xanthan gum that they are degraded by these bacteria only, okay, which are present in colon. So cellulose acetate or guar gum are dissolved in the less acidic pH in intestine and above pH. Okay, cellulose acetate, cellulose acetate phthalate, these are the things, these are the polymers which are used in the colon targeting. So you will have to discuss, you will have to have that particular knowledge or particular information that what is the property of polymer. Then only you can use it in your dosage form. We have discussed this pH sensitive smart polymeric insulin delivery. We discussed, remember, insulin is there. In the normal case, pH 7.4, insulin is remaining there. What happens when in the system, when the pH lowers, when it is lowering, when the glucose will be higher, glucose will be converted into the glucuronic acid, pH will be lesser there, and that case delivery system that which is meant which is made by the EVA copolymer is sense the change in the pH, and it has the inherent property of get diffused, and erosion occurs into the polymeric matrix, and the insulin is released into the system, and the glucose transport is increased and the glucose level comes down. Again the pH reaches to this 7.4, then again this material becomes integral. The integration only occurs, that erosion is stopped and the insulin release is stopped. So it is a perfect smart system of insulin. Now I'm just giving you quickly the examples how you can learn this. For example, sodium CMC, they are available in two grades, low viscosity and high viscosity. It produces a clear solution in both hot and cold water, which are stable over a pH range of 5 to 10. It is anionic, so it is incompatible with polyvalent cations, and the acids the acid will be precipitated at low pH. Heat distillation reduces its viscosity. They are widely used up to 1% in topical, oral and parenteral products. So these are the monograph. You can say it is your inbuilt monograph. What kind of information you want, you can enlist them. Let's take another example. The microcrystalline cellulose, they are crystals of colloidal dimensions which disperse readily in water but are not soluble to produce thixotropic gels. It is a widely used suspending agent, and the rheological properties of its dispersion can often be improved by the incorporation of additional hydrocolloids, like in particular CMC, methyl cellulose, hydroxypropyl methyl cellulose. These stabilize the product against the flocculating effect of added electrolyte. So you can have prepared this kind of ready monograph for you. Another example, very important, carbopol, you can say them. Carbopol is a brand name of carbomers. They are synthetic copolymers of acrylic acid and allyl sucrose. At concentration of up to 5.5%, they are used mainly for external application, although some of the grades can be taken internally. Upon dispersion in water, it forms acidic, low viscosity solutions which, when adjusted to a pH between 6 and 11, become highly viscous. So these were simple examples. So let's learn about the polymers with respect to the chemical nature, including its molecular weight, physical properties, solubility, grades, response to the change in pH, temperature, etc. If particular property is there with respect to the pH, temperature, or any other, you must have the information about it. At least the polymers available in your lab must be you must be well versed about their properties. Okay, and major applications you must. So chalk out these points for the common polymers, at least which you are having in your lab and which are commonly used in the novel drug release system. Sometimes they are asked in a short note. Remember this thing. You may be asked that write a note on the hydrophilic matrices forming polymers. You may be asked the short note on the carbopoles, carbomers. Okay, so you must be well versed with this kind of polymers, and with respect to the number of scoring of the questions, you can put your answers. Okay, it might not be case that it is not expected that you will reproduce the chemical structure, but at least you must have an idea about the solubility, about a specific property of the polymer with respect to the pH or any other property. Okay, so these are the some references, and I like this book, Handbook of Pharmaceutical Excipients, CRC Press. It's a encyclopedia, you can say, of the polymers. It is a wonderful book. Each and every polymer you will get in it, and some other references. So let me summarize what we learned. Polymer is a very big topic. We just try to wrap it in the from exam point of view, that what you should learn. These are monomer units joined together. They may be classified on many bases. They are needed in dosage form, novel drug system, and targeted drug delivery. They modulate the pharmacokinetic, alter the pharmacokinetic of a drug when they are put into the drug delivery systems, and they can manipulate the onset and duration of action. The selection of polymer is governed by various factors, including the properties of drug, properties of polymer, type of product desired, type of release desired, and uh, some other factors which may be specific to the need. Okay, so this is all about the polymers. We will be coming back with our next lecture in the series of our lectures in the NDDS. Hope you are enjoying our lectures. Stay tuned with us for the next lecture. Thank you for being with us. We are coming back with the new lecture soon. Happy learning.